Ramachandran plots are a useful tool for taking a snapshot of how a protein is folded. So let's break that down. We talked about the peptide bond, and we said that the peptide bond does not rotate, which is true. So here's our peptide bond. It does not rotate. However, the bonds on either side of it, here and here, are single bonds, and they do rotate. So we could also draw those as the bonds here and here on either side of the alpha carbon. So rotation is permitted around that bond between the alpha carbon and the nitrogen in the peptide bond. So that's called the phi angle, or the phi bond. And then it's also, rotation is permitted between this carbon, the alpha carbon, and the carbonyl. And we're going to call that the psi bond, and rotation around that will be called the psi angle. So those are the Greek letters phi and psi. They describe rotation around this bond and this bond. So another word for this is torsion angle, which describes the rotation around the phi and psi bonds. So if we look down the axis of that nitrogen to alpha carbon bond, we could potentially try to line up these carbonyl groups, right? And when they're completely lined up, then our phi angle is minus 80. And then as we move them away from being lined up, we can get a phi angle that we can measure by the torsion angle. The same kind of thing is going on here for the psi bond. So if we line our polypeptide up by that carbonyl to alpha carbon bond and we look down it, we could line up these amine groups. And if they're completely lined up, then our psi angle would be 0. And then as we move them away from each other by rotating along that single bond, then we get a psi angle that is not 0. Another way to look at it is, here's a polypeptide chain. So we've got a couple different amino acids in it. Here's a peptide bond, here's an alpha carbon, here's the next peptide bond, another alpha carbon, etc. And remember that we said that these 6 atoms right here lie in a plane. So we're going to describe the rotation around phi right here and psi right here. And then there's another unique phi and psi angle for the next amino acid here and here. And another unique phi and psi angle for the next amino acid right there and there. So together, these phi and psi angles describe the rotation of each amino acid relative to its neighbor. We're going to organize these in what's called a Ramachandran plot. So a Ramachandran plot describes the torsion angles for every amino acid in your peptide or in your protein. So the way this works is that the phi angle is plotted on the x-axis and the psi angle is plotted on the y-axis. So if I look at a specific amino acid in my peptide, I could measure the phi angle and the psi angle and put a dot, plot a single point for that amino acid. And then I measure the next amino acid's phi and psi angles, and they are certain numbers, and I make a dot for that amino acid, etc. So I would go along filling this out with dots until I've measured for the entire protein, and that's how a Ramachandran plot is built. So what do we think a Ramachandran plot will look like for the average protein? Do we think this space will be randomly covered in dots? Do we think only certain parts of it will be covered in dots? What do we think this is going to look like? Well, it turns out that these Ramachandran plots tend to follow specific patterns because of bond geometries that are favorable or unfavorable. So instead of doing this with the dots, we can shade the regions that have a lot of dots in them. So if you see a darker region in your Ramachandran plot, that means that's a very common set of angles, phi and psi angles, for amino acids to occupy. So a lot of amino acids are occupying this space here and this space here, some here and some over here, and then some never occupy this geometry. So why is that? Again, because certain bond geometries are going to be preferred, and some will be really not preferred because it leads to steric clashes or overlaps in the atoms. So for example, this right here shows if the phi is 90 degrees and the psi is negative 90 degrees, we see a lot of clashes between our carbon, would that be a carbonyl? Yep, our carbonyl here and our R group here, right? These two atoms are trying to occupy the same space. So they're not going to want to do that very often. So that leads to certain preferred and not preferred geometries. And then what's really cool is we can trace specific secondary structures and measure the phi and psi angles in that secondary structure. And now we start to understand why certain geometric conformations are preferred. So for example, if we trace out the phi and psi angles that are present in parallel beta sheets, we find that this is the geometry of the peptide backbone. If we look at anti-parallel beta sheets, it's pretty close. If we look at the right-handed alpha helix, we're going to get phi and psi angles over in this region. If we look at the left-handed alpha helix, we're going to get phi and psi angles over here. And again, the left-handed alpha helix is less common than the right, and that's why this region is darker shaded than this region. We see some other things here like the collagen triple helix, right? So altogether, we can see how the secondary structure drives what phi and psi angles are preferred in our polypeptide backbone. And we can see that show up in our Ramachandran plots. So altogether, what do we learn from Ramachandran plots? One thing we learn is that some phi and psi angle combinations are very unfavorable because of steric crowding of backbone atoms with other atoms in the backbone or in the side chain. That's why we don't see a lot of amino acids occupying geometries in this quadrant. The other thing we learn is that some phi and psi combinations are more favorable because it gives them a chance to form favorable hydrogen bonding interactions along the backbone. So those are going to be those favorable hydrogen bonds in our parallel and anti-parallel beta sheets and in our alpha helices. So You can connect this concept for yourself. In your own words, explain why the bottom right quadrant of a Ramachandran plot is typically empty. And another one, draw the Ramachandran plot you would expect to see for the iron storage protein ferritin, which is shown here. And as you can see, it is completely made out of alpha helices. So what would you expect that Ramachandran plot would look like?